Hello students, I am Professor Sanjay Bhargav, MSc PhD with a teaching experience of more than 38 years. I welcome you all to my YouTube channel Physics with Dr. Sanjay Bhargav. This channel will provide useful and authentic physics related material for state board exams of class 12th, Neet, IIT-JEE, CUET exams. For this, please visit and subscribe this YouTube channel at the rate Sanjay Bhargav 6807. For any query, you can mail at sanjaybhargav 167 at the rate gmail.com. In my first lecture, we are going to study about electrostatics. In this first lecture, we will cover what is charge, what are the important properties of the charge, how to calculate the force between the two charges with the help of Coulomb's law. Let us begin with first, what is electrostatics? So electrostatics can be defined as branch of physics in which we study about electrical forces, electrical fields and potentials produced by the stationary charge. As you can see, the word electrostatic is made up of two words, electron and static. Electron is a representation of a charge, while static means at rest. So in electrostatics, we study properties of charges at rest. Now, first question that comes to my mind is, what is charge? Charge is a scalar physical quantity associated with bodies having mass and which is used to describe electric and magnetic interaction. So the first word says scalar physical quantity. That means scalar as it adds according to the laws of scalar addition. Physical, that means charge is a measurable quantity. Associated with bodies having mass, it means that charge can only be given to the bodies possessing mass. And what is the utility of the charge? It is used to describe electric and magnetic interactions. What are the important properties of the charge that we are supposed to know? The first property that we can say is charge is a derived physical quantity with an SI unit coulomb and its dimensions are ampere power 1 T power 1. Charge is a scalar quantity because it adds according to scalar laws of addition. Simple laws of addition are utilized to add and subtract charge. Charge is always associated with massive bodies. That means charge can only be given to the bodies which possess mass. For example, we have certain bodies with zero rest mass like photon, neutrino, antineutrino. All these bodies have zero rest mass and therefore no charge can be given as their rest mass is supposed to be zero. Then there is a set of examples of bodies which possess mass, like we can have electron. What is the mass of the electron? 9.1 into 10 raised to power minus 31 kilogram. What is the charge on the electron? Minus 1.6 into 10 raised to power minus 19 coulomb. Electron has mass, therefore carries a charge. Similarly, proton. Mass of the proton is 1.67 into 10 raised to power minus 27 kilogram. And what is the charge on the proton? 1.6 into 10 raised to power minus 19 coulomb. So they represent a body which possesses mass and therefore can also be given charge. We can always think about a body called neutron. Neutron, mass of the neutron is known to us, but what is the charge on the neutron? That is supposed to be zero. That means every massive body necessarily may not carry charge, but every body possessing charge would definitely have mass. We have two types of charges, a positive charge and a negative charge. Now, a body which gains electrons will acquire negative charge. Similarly, a body which loses electrons will acquire equivalent positive charge. A basic question that comes to our mind is, on charging, does the mass of the body change? And the answer is yes, but by a very negligible amount. Let us say we have a body of mass m. When it becomes negatively charged, it means it has acquired certain number of electrons, so the mass becomes m plus delta m. Similarly, a body which acquires positive charge would lose certain number of electrons, and therefore the mass becomes m minus delta m. What does delta m represent? It is change in mass due to transfer of electrons. And remember, delta m is usually very small. So we normally do not talk about it, we normally ignore it. Charge can always be transferred from one body to another. Then, as per the conservation, charge lost by one body would be equal to the charge gained by another body. Another property of charge that we understand, like charges, they repel each other, while opposite charges, they attract each other. Now, the basic question is, what is the sure test of electrification? And the answer says, repulsion is the sure test of electrification. Why? Because repulsion happens only between two similarly charged bodies, while attraction may result between a charged and an uncharged body, and attraction also takes place between two oppositely charged bodies. So attraction is possible under two circumstances, a charged and an uncharged body and two oppositely charged body, but repulsion is unique, only possible between two identically charged bodies. That is why we say repulsion is a sure test of electrification. Another important property of charge is the conservation of a charge. And how do we say about it? For an isolated system, the total charge on the system is always conserved, which means the total charge on the left hand side and the total charge on the right hand side are supposed to be equal. Let us pick up an example in which a neutron converts to a proton with the emission of a negatively charged electron and an anti-neutrino. So what is the total charge on the left hand side? Neutron carries zero charge. And on the right hand side we have plus E and minus E as the charge. So the net charge on the RHS is also zero. Since the total charge on the left hand side and right hand side are equal, we can say such processes are possible in physics. We can pick up another example. Uranium-238 decays to thorium-234 with emission of an alpha particle. What is the total charge on the left hand side? 92 times the electronic charge. And what is the charge on the right hand side? It is 90 times E plus 2 times E, which would be 92 times E. Another example that you can talk about is normally the process of fission. Uranium-235 bombarded by slow moving neutron gives barium, krypton and 3 neutrons. What is the total charge on the left hand side? 92 times the electronic charge. And on the right hand side, 56 times the electronic charge plus 36 times the electronic charge, once again giving me the total of 92 times electronic charge. Hence, all these processes exhibit total charge on the left hand side is same as the total charge on the right hand side. Therefore, the equations are physically permissible. Another property of charge is quantization of a charge. Charge is a quantized physical quantity. The total charge on a body is always an integral multiple of charge on an electron, that is 1.6 into 10 raised to the power minus 19 coulomb. So the basic unit of charge is charge on an electron, which is 1.6 into 10 raised to the power minus 19 of coulomb. So what is the charge on a body? Q can be written as N times E. Remember, N is an integer and E is 1.6 into 10 raised to the power minus 19 of coulomb. In physics, are all charges possible? Let us check. In the first question, we ask a question, is charge 1.6 into 10 raised to power minus 18 coulomb possible? So 1.6 into 10 raised to power minus 18 can be written as 1.6 into 10 raised to power minus 19 into 10 power 1, that is 10 times E. The total charge is an integral multiple of E. So 1.6 into 10 raised to power minus 18 coulomb is possible. Now let us check. Is the charge 1.6 into 10 raised to power minus 20 coulomb possible? So 1.6 into 10 raised to power minus 20 coulomb can be written as 1.6 into 10 raised to power minus 19 multiplied by 10 raised to power minus 1, which is equal to 1 by 10 of basic unit of charge. As per the quantization principle, fractional charges are not possible. So charge 1.6 into 10 raised to power minus 20 coulomb is not possible. Another question that we need to answer is how many electrons are required to produce a charge of 1 coulomb. So number of electrons required, N would be equal to Q by E. Charge is 1 coulomb and E is 1.6 into 10 raised to power minus 19 coulomb, which gives me a number 6.25 into 10 raised to power 18. So 6.25 into 10 raised to power 18 electrons will be required to produce a charge of 1 coulomb. That is why we normally say 1 coulomb is a large unit of charge. Now, how can the charges be produced? Charges can be produced by 3 different methods of conduction, induction and friction. In conduction, what happens? Uncharged body is made to come in contact with another charged body. Charge always flows from a body of higher concentration to a body of lower concentration, and the second body also becomes charged. In induction, an uncharged body is brought close to the charged body. They are not in contact with each other. They have a small distance between them. Equal and opposite charge would be induced in the body. So that is action at a distance. In friction, what happens? The two bodies are made to rub against each other. Electrons are transferred from one body to another. So one of the body which gains electrons becomes negatively charged and another which loses electrons becomes positively charged. How can charge be measured or detected? Charge can always be measured or detected by an instrument called gold leaf electroscope, a ballistic galvanometer, voltmeter or an electrometer. Now, in the basic properties, what we have said, like charges, they repel each other. Opposite charges, they attract each other. Now the question comes up is, with what force do they either attract or repel? This answer comes through Coulomb's law. What does the Coulomb's law basically say? The electrostatic force of attraction or repulsion between two stationary point charges is proportional to the product of magnitude of the charges and inversely proportional to square of the distance between their centers. The direction of the force is always along the line joining the center of two charges. Let us pick up a system of two charges Q1 and Q2 which are separated by a distance r. Now what does the Coulomb's law say? The force is proportional to product of the magnitude of the charges. So F proportional to Q1, Q2. It says force is inversely proportional to square of the distance between their centers. R is the distance between their centers. So force is also proportional to 1 upon r square. Combining the two, I can write as force proportional to Q1, Q2 upon r square. To remove the proportionality sign, I require a constant K. So F would be equal to K Q1 Q2 upon r square, which would be equal to 1 upon 4 pi epsilon 0 Q1 Q2 upon r square. What is K here? K is electrostatic constant with a value 9 into 10 raised to power 9 Newton meter square per Coulomb square. K can also be written as 1 upon 4 pi epsilon naught. And what is epsilon naught? 8.85 into 10 raised to power minus 12 Coulomb square upon Newton meter square. It represents permittivity of free space. That is, vacuum. Now question is, what is permittivity? So permittivity is measure of ability of medium to allow electric field lines to pass through it. Measure of ability of medium to allow electric field lines to pass through it. Now, what are the different properties of electrostatic force? We just said electrostatic force can be attractive or repulsive, and what would that be decided by? It is decided by the polarity of the charge. Identical charge, they repel each other. Opposite charge, they attract each other. Electrostatic force is a medium dependent force. The force between the two charges is maximum in vacuum because the value of epsilon for different medium comes out to be different. That is why we say that it's a medium dependent force. So I can say epsilon is different for different medium. Electrostatic force is a conservative force. What are the properties of the conservative force? The work done by the conservative force along a closed path is zero. The work done by the conservative force depends only on initial and final positions. So, electrostatic force is a conservative force obeying all such properties. Electrostatic force is a central force because it always acts along a line joining the center of the two charges. Let us just see the example here, Q1, Q2. Q1 can exert a force on Q2 and that would be to the right. Similarly, Q2 can exert a force on Q1 and that would be to the left. But both the forces are along the line joining the center of the two charges, and that is why we call electrostatic force as a central force. Electrostatic force forms a pair of action and reaction forces. It can always be proved. We pick up an example, a system of two charges, Q1, Q2 is greater than 0. That means either both are positive or both are negative. I can calculate what would be the force on charge Q1 due to Q2. That can be F12 K Q1 Q2 upon R square, and the direction is from 2 to 1. So this gives me the direction F12. Similarly, what is R21? It's a unit vector from the charge Q2 to Q1. Similarly, force on charge Q2 due to Q1 would be K Q1 Q2 upon R square, and see the force is on 2, and that is why the direction of the force is to the right, and it is from 1 to 2. That is what we find here, K Q1 Q2 upon R square R12, and R12 is nothing but a unit vector from the charge Q1 to Q2. Here F12 and F21 are equal in magnitude, opposite in direction, and therefore form a pair of action-reaction force. Since the two unit vectors are opposite in direction, we utilize the negative sign. They have the same magnitude, that is 1, but the directions are opposite, and therefore the forces F12 and F21 are equal in magnitude, opposite in direction. Or we can also write it as F12 plus F21 would be equal to 0. What does that mean? It says the equation shows that sum of internal forces F12 and F21 is equal to 0. Thus, net force acting between a pair of charges is 0. A very important result. Net force acting between a pair of charge is 0. Now, we defined first permittivity of free space, and we said that the value of epsilon for different medium will come out to be different. So we need another quantity called relative permittivity, or also known as dielectric constant. For that, let us calculate force between charges Q1 and Q2 in vacuum. So force in vacuum would be equal to 1 upon 4 pi epsilon 0, permittivity of free space. Q1 Q2 upon R square. Similarly, you can calculate force between same two charges in a medium of permittivity epsilon. So force in presence of medium would be 1 upon 4 pi epsilon Q1 Q2 upon R square. Let us calculate the ratio of force in vacuum to force in medium. That would be equal to epsilon upon epsilon naught, and that ratio is called as permittivity, that is relative permittivity, which is also called as dielectric constant. Dielectric constant is written with K and is pronounced as kappa. So what would be the force in a medium? From this equation, force in medium would be equal to force in vacuum to epsilon r. Epsilon r is a pure number. It's a unitless, dimensionless quantity because it is ratio of two permittivities. It's a pure number. That's what we stress upon. It has different values for different medium. For air, the value of epsilon r is equal to 1. For water, epsilon r is 81, and for metal, epsilon r is infinite. Now let me define relative permittivity. How can I define? It can always be defined as the ratio of two permittivities, or it can be defined as the ratio of the two forces. So the first definition here says defined as the ratio of permittivity of medium to permittivity of free space. It's also defined as the ratio of electrostatic force between two given charges separated by a given distance in a vacuum to the force between same two charges separated by the same distance in a medium. So two definitions here, one in terms of ratio of permittivities and the second in terms of ratio of forces, force in vacuum to the force in medium. What is the unit of charge? To define the unit of charge, let us say as per Coulomb's law, force would be equal to K Q1 Q2 upon R square. Let us say Q1 Q2 is 1 coulomb and R is equal to 1 meter. In that case, force would be equal to K, and what is the value of K? 9 into 10 raised to power 9. So what is 1 coulomb of charge? 1 coulomb is that charge which when placed at a distance of 1 meter in vacuum from another similar stationary charge repels it or is repelled by it with a force of 9 into 10 raised to power 9 Newton. So the two charges are 1 coulomb each, separated by a distance 1 meter. If that happens, then the force between the two charges would be 9 into 10 raised to power 9 Newton. What is the CGS unit of charge? In CGS we have two units, that is stat coulomb and the absolute coulomb. ESU, it means electrostatic unit, electrostatic unit of charge. And what is EMU? It is electromagnetic unit of charge. So 1 coulomb would be 3 into 10 raised to power 9 ESU, and similarly it will be equal to 1 upon 10 EMU. So EMU upon ESU would be 3 into 10 raised to power 10. Since we are in the CGS unit, so the speed of light is nothing but 3 into 10 raised to power 10 centimeter per second. So EMU and ESU, the ratio is equal to speed of light. Now just to check the concept of relative permittivity, we answer a question: find force between two charges Q1 and Q2 when a metallic plate is kept between them. So we just found out force in presence of medium would be equal to force in vacuum upon epsilon r. So force in presence of metal would be force in vacuum divided by epsilon r for the metal. And what is the epsilon r for metal? Infinite, and 1 upon infinity is 0. Thus force between two charges Q1 and Q2 becomes 0 when a metallic plate is kept between them. This gives me a method to reduce the force between the two charges 0 by just placing a metallic sheet between them. So I hope this video would be useful for all of you. Thank you very much. Look forward to you all in the second video.